from now on, I'm going to deal with a little bit more advanced topics with the quantum information. And then the first topic I'm going to reconsider is the third postulate of the quantum mechanics. Third postulate of the quantum mechanics mainly talk about the measurement of the some given quantum state, and then the description we are going to deal with today is a little bit unusual in the sense that even the quantum mechanics taught for the physics major students are not generally this kind of concept, this kind of new concept are not generally covered in the general textbook. So, so let's begin with what we learned in the previous lectures. So, yeah, in the previous description, what we said was if some particle is described by some vector in a Hilbert space, and then let's say it is psi, and then in that case, whenever we are considering about some measurement, we will have some Hermitian operator, and then in this case we call it as omega, and then we simply just assume that this and then this Hermitian operator is generally called as observable. So and then what happens with the measurement is that because this observable operator is Hermitian operator, so we will have also orthogonal eigenvectors and then corresponding eigenvalues. And then whenever something is measured for this quantum state, then the result of measurement will be one of the eigenvalues, and then the probability of measuring this some eigenvalue is proportional to this formula. And then in this case, the omega sub I is the orthonormal eigenvector corresponding to this eigenvalue. So what the first statement says is that what kind of value we can measure, and then what is the probability we can measure such kind of state. And then the second statement was saying that it is mainly talk about what is the result, or what happens to the quantum state once we make some measurement. And then we learned that the quantum state will turn into the corresponding eigenvector right after the measurement. Now, what we are going to do is we will use the a little bit different definition, which was introduced in the section 2.2.3 in our main textbook. And what this section says was quantum measurement is defined by a set of measurement operator, m sub m. And then this operator is different from this this omega. So yeah, again, this omega was called as observable, while we call this this operator as a measurement operator. And then in this case, in the previous case, we had only one Hermitian operator, while in this new description, this new operator is not just one, but if we have if we have an option of obtaining different number of the measurement result, then we will have corresponding operator. Yeah. So yeah, let's say that if we have an option to measure either 0 or 1 or 2, then there will be always corresponding as M0, M1, and M2. Moreover, different from this operator, this new measurement operator doesn't have to be Hermitian or some other restriction. Well, there is one restriction which I will say later, but yeah, here, yeah, it mainly doesn't have too much of the restriction. And then of course, because this is operator, this operator will act on the Hilbert space of the quantum state. And then the this again, this subscript will mean the different outcomes. and then yeah. So if you compare with this this description, then here, yeah, we just define that what kind of measurement value we will obtain here, and then yes, then the probability to measure one of these options, it corresponds to this kind of formula. So yeah, again, yeah, this is the initial quantum state, and then if we have some corresponding measurement operator for each different value, then the probability to measure such kind of value is can be obtained by this formula. And finally, similar to this description, we should also consider what will be the final state, and then the final state can be obtained by applying the this one of the measurement operator on the quantum state, and then the overall state should be normalized. You can see that this factor is just introduced in the denominator because we want because if you have this kind of new vector or this new vector, then you want to normalize, and then the way you can normalize is calculating the magnitude of this one. Yeah, so yeah, this is exactly what we are doing for normalization. And then I actually mentioned that there is one restriction for these new measurement operator or set of the measurement operators, and then the requirement looks like this one, and then it is called as a completeness equation because the requirement comes from the concept that if each of these represent the probability, then we know that the total sum or summation of all the possible probability should become 1. So if we add all of them, then it should become 1. But because of this definition, if we plug in this formula, then it will be it will look like this one. And then because this bra is multiplied to all the terms, and then this cat is also applied to all the terms, so we can in principle recollect or factor out these two bra and cat, and then the remaining part can be collected in this this way. And then because the entire expression here should become 1, and then because this psi, these vectors are already, we are assuming that these are already normalized. So the only way to satisfy this requirement is just adding all the adding all the this kind of form, and then the this kind of so whenever we have the some set of the measurement operator, then for each of them, we should multiply the Hermitian conjugate of the corresponding operator, and then we sum them together, and then this one should be the same as the identity. I know that this kind of new formulation of the third postulate is somehow weird, and then I remember that when I first saw this kind of definition, it was completely different from what I generally had. So I also had a little bit hard time understanding this one. So let's first check with some simplest example. So here I'm just providing some example of these two measurement operators, and then I can claim that this is a good measurement operator according to the new definition of the third postulate, because the first thing we have to confirm is that the summation of this formula will become identity, and then it is obvious because if we have the definition of m sub 0 like this one, then the Hermitian conjugation of this one is the same. So it is, and then because here this operator by itself doesn't have to be Hermitian, but we intentionally just chose the Hermitian operator so that all the discussion might be a little bit easier. So if we have this kind of Hermitian operator, and then it will just becomes like a square of the m sub 0, and then we know that 0, 0, 0, and then the multiplication of this, the square of this operator will become just 0, 0 multiplied by 0, 0. So they will just be, this one will become just 1, so it will become 0, which is the m sub 0 again. Similarly, for the m sub 1, yeah, the Hermitian conjugate of m sub 1 and then the m sub 1 will be just the m sub 1. And then to check the completeness relation, then it is just the summation of these two basis vector. And then you remember that when we discuss about the two-dimensional Hilbert space, then this kind of summation was called as the completeness relation. And then we know that the summation of all the possible bases in this shape will corresponds to identity operator. So yeah, this the summation of this form will become identity operator. So that's the only requirement necessary for the set of the measurement operator. So yeah, this is a well-defined measurement operator. And then let's see what happens if we apply the measurement operator to this kind of initial state. So yeah, the first thing we want to know is what is the probability to measure 0? And then the measurement operator for zero value is like this one. And then this was the formula which I introduced in the previous page. And then we know that this is just m sub 0. And then once we plug in this expression to here, then this 0 will only act on, so if I just plug in 0, 0, and then because the psi is the A0 plus B1, so only this term will survive, and then this term will become 0. And similarly, if I just multiply psi on here, then there will be A star coming from the left-hand side, left part. So the result will be just the square of the absolute value of A. And similarly, if I apply the same formula for the P of 1, then it will be like this one, and then you can easily check that the result will come out like this one. So yeah, we can see that this new set of the measurement operator corresponds to just measuring the given quantum state in the measurement basis of the 0 and 1, or we call it as a computational basis. So so in the previous case, whenever we want to describe the measurement in the computational basis, we started with the observable operator, which will have the 0 vector and 1 vector as the eigenvectors. But here, we didn't think about anything like eigenvector, and then we just define the set of the measurement operator like this one, and then the result seems to be same. And moreover, what about the final state after the measurement? And then let's say that if we obtain the 0 value, then according to formula which I introduced in the previous page, this was the formula for the quantum state after the measurement. And then as you can see here, if I apply this M0 on the psi, then we know that this part will just come out as A times 0, and then this denominator corresponds to this part. So it is square root of the A a absolute value. So yeah, it will become like this one. And then you might say that this is different from what we are expecting from the perspective of the previous definition of the measurement, but it is not, because all it says is that the magnitude by itself is not the magnitude is 1, and then the only difference is that the final state might have some kind of phase factor, but we know that if the final state looks like this one, then the phase in front of 0, it works as just a global phase, so we can just ignore this part. So the final state here is the same as is just 1, as just the 0, which is exactly the same as the previous definition of the measurement. And then similarly, if we apply the case for the measurement result of 1, yeah, then the final state will be just 1. Then you might wonder, why do we need a new definition of the so in the previous page you saw that we can reproduce most of the same result we can obtain with the previous definition of the measurement. And then so why do we need new definition of a measurement, a set of the measurement operator compared to the previous case? And then the reason is, if we start with the new definition of the measurement, then we can do some more general concept for the measurement. And then also when we have to treat the measurement more mathematically, then it becomes much simpler. So yeah, let's see why how it can be helpful in formulating a lot of other parts. So yeah, let's say that all of you are familiar with the concept that if we have two quantum states like H and D, then it is obvious that we cannot completely distinguish these two states, because there is an overlap between these two bases, so they are not orthogonal to each other. So non-orthogonal quantum state cannot be distinguished with the certainty. So there will be always some kind of uncertainty if we are just trying to measure all the given quantum state. And then it is intuitively obvious, but that how can you prove this kind of relation with just using the original old definition of the measurement? Of course, you can probably do that with some other way, but the proof of this one might be a little bit easier if we use the new definition of the measurement. So before I start to prove that the non-orthogonal quantum state cannot be distinguished with the certainty, let me just start with the case when we are just given all the orthonormal states. So yeah, let me prove that orthonormal state can be always distinguished without any uncertainty. And then yeah, of course, yeah, it is obvious for all of you, but yeah, let me just try to prove that formally. So suppose that we have n orthonormal state, but in principle, yeah, what we want to do is distinguish between these n orthonormal states. But yeah, so let's say this n corresponds to 3, but the overall dimension of the Hilbert space might be something like dimension is 10. So yeah, even in such kind of case, how can we prove that the orthonormal these three orthonormal states can be always distinguished with the certainty? And then yeah, so the way we can start our proof is the following. So let's define new measurement operators corresponding to these three cases. So so there will be M1, M2, M3 measurement operator. However, we know that because this one is the entire dimension of the Hilbert space is 10, so we might have also other state which cannot be described by only these three orthonormal states. And then in that case, the point is we are not interested in other remaining seven dimensions. So we will define a new measurement operator corresponding to the rest of the dimensions. So because we only define the measurement operator corresponding to our interested three orthonormal bases, not bases, but the orthonormal states. So let's say that the M0 will correspond to the measurement of the rest of them. Then from M0 to M4, M3, sorry, here I'm just assuming that small n is 3. Then these four measurement operator will always satisfy the completeness relation, which I showed you in the first page. And then what we can be sure is that if the state, if the one of the state, if the given state is prepared in one of these three states, then we know that if I apply this this formula for the probability to measure the ith measurement, like M2 or M3, then the formula is like this one. And then if the original state is already prepared in this state, while if our measurement operator from 1 to 3 is defined in this way, then this value will be just simply 1, which means that 100%. And then it is intuitive that if we are given m's vector, like psi 2 is given, so if I just assume that I equals 2, sorry. So if I equals 2, then when I'm given psi 2, then it is obvious that we are expecting that the probability to measure measure the I equals 2 should be 100%, and then it is obvious from this relation. So we just what we did is we just proved that if we have only orthonormal basis, orthonormal quantum state, we want to distinguish, then we can always distinguish them with the 100% certainty. So it is a trivial proof, but what is important is here the obvious, so if we just started with the new definition of the measurement, then the mathematical proof like this one becomes straightforward. So the previous proof was trivial, or the case was trivial. So let's also start with the proof that if the given states are not orthogonal to each other or orthonormal to each other, there is no guaranteed quantum measurement capable of distinguishing those two states with 100% or without uncertainty. So how can we prove that? In this case, we are going to use the proof by contradiction. So we will first assume that it is actually possible to there is some kind of measurement operators or a set of the measurement operators which can distinguish the not orthonormal states. So and then we will call such kind of new measurement operator as m sub j. And then in this case, j can be 1, to something like let's say 10, and then there will be always some kind of corresponding measurement operator, m sub 1, m sub 2, and so forth, like 10 m10. And then given that we have and then with this kind of measurement operator set, we should be able to distinguish two non-orthogonal state, like psi 1 and psi 2. So they are not orthogonal. Yes, I'm just assuming that they are not orthogonal, like this. And then what we want is we want to have some kind of function, one-to-one functional relation. So let's say that if I measure m2, or the measured value is we obtain the measurement result of 2, then we might want to have some kind of function that 2 will be mapped to psi some 5, and then psi 5, and then let's say that if we measure 3, then it will map to the psi 1, and then there will be some other combination, and then there will be let's say if I measure 1, then it will correspond to psi 2, or something like this one. So this is what we hope. And then for this case, I will define that the f of 1 is 2, and then f2 is 5, and f3 is 1, or something like this one. So there, we are expecting that there will be some kind of one-to-one functional relation. And then now, what we know that is that because psi 1 and psi 2 are not orthogonal, so in principle, psi 2 can be expressed as the summation of some psi 1 and some other vectors like this one. And then the point is that alpha cannot be 0. So under this assumption, we are assuming that there is some k, and then in this case, I will say that the k is 3, like this one. So k is 3, and then if we apply the this measurement some third measurement operator, and then if I apply this measurement operator to the psi 1, given psi 1, and then we are just assuming that the probability to measure the k, or k equals 3, is non-zero, which means that because we are trying to figure out some kind of one-to-one correspondence, or well, I should one-to-one correspondence, then we expect that the f of 3 will correspond to the first state, and then we are expecting that we hope that if this first assumption is true, then we hope that whenever we measure the value 3, then I should say that if I'm given psi 2, then I should not obtain the measurement value of 3, because if I obtain the measurement value of 3, then there is an ambiguity whether the measured state is psi 2 or psi 1. And then because we already decide that whenever if we measure the value of 3, then there is some chance that that state will be psi 1. So under this situation, then we know that if we calculate the probability to measure k, or 3 for the given psi 2, then the probability can be calculated by this way. But what this means is that so this state means that Yeah. So this can be represented like alpha star plus phi beta star, and then it is M3 dagger, M3, and alpha psi 1 plus beta psi 2, like this one. And then finally, yeah, this will be expanded as psi 1. Yeah, so here is alpha star, alpha, and psi 1, M3 dagger, M3 psi 1, and there will be additional terms. But we know that we already assume that this term won't be 0, because that's our assumption here. And then this alpha won't be 0 either. So this value, this term will be at least larger than 0. And then what that means is that the overall calculation of this probability won't be 0 either, which means that even if we are given psi 2, there is some chance that we will measure value of k, or let's say value of 3, and then once we obtain those 3, then we don't know whether we should interpret that one as 1 or 2. So even if we start with the assumption that with the new measurement operator set, then we should be able to distinguish psi 1 and psi 2. But it turned out that there will be some kind of ambiguity for this case. So so the assumption is wrong. And then that's how we can prove that in quantum mechanics, we cannot distinguish two orthonormal quantum state with 100% certainty. So again, this kind of statement is intuitively obvious, but if you are supposed to prove such kind of relation, then with the old definition of the measurement, then it might be a little bit cumbersome to prove. But with the given with the new definition of the measurement, then it is much more elegant or more convenient. So and then here my proof was not completely rigorous, because I didn't want to spend too much of time proving this obvious result. And then if you are more interested, then you can actually refer to the box 2.3 on the pages 87 in the main textbook. Another application of the new measurement definition is error. It is can be error correction code. So we during when we covered about the quantum error correction code, I said that this kind of circuit can detect one bit flip, and then but yet it is if we just want to confirm whether we can be able, we should whether we will be able to detect one bit flip, one qubit flip or not. Until we construct this kind of circuit, it is not obvious whether we can do that. However, to come up with this kind of new circuit, then you actually need some kind of background in the classical error correction code. However, let's say that your interest is not to develop the error correction code by error detection circuit by itself, but what you first want to confirm is whether quantum mechanically whether it is possible to detect a single qubit error, bit flip error or not. And then if you start with this kind of measurement operator definition, then you know that all of these will satisfy the requirement for the measurement operator set, which was something like M sub M dagger M should be complete, like this one. So, and then if you plug in all these four definition to this formula, then you will immediately check that they will satisfy this relation. And then what that means is that even though you don't know how to construct this kind of circuit, you can be sure that the quantum mechanically, the distinction of the bit flip error, one bit flip error can be implemented. And then the reason you want to confirm such kind of thing in advance is if the quantum mechanically such kind of distinction is not allowed, then there is no reason why you will spend more time in coming up with a new circuit to implement such kind of new error correction code. So up to now, I said the new definition of the measurement is more general compared to the original definition I gave you. And then the original definition I gave you is generally called as a projective measurement. And then the projective measurement goes like following. So in that previous definition, we generally assume that there will be Hermitian operator called as observable M, and then the measurement result will generally determined by the eigenvalue of this observable operator. And then in this case, if for example, if I have the omega 0 eigenvalue with the 0 state, and then if I have the eigenvalue 1 with the state 1, then we know that this the Hermitian operator, which will have this eigenvalue with this eigenvector and this eigenvalue with this eigenvector, then they can be always constructed like this one. So yeah, it is well known. So yeah, so in the previous projective measurement, this is the starting point of the measurement. However, whenever we have the projective measurement case, then it can be always reformulated in terms of a new definition. So and then yeah, we generally call this kind of combination as the projection operator. So let's say that this is a P0, and then this definition is this combination is P1. So then we can consider that P0 and P1 are the set of the a new set of the measurement operator for the new measurement. And then in that case, the corresponding measured value will be lambda 0 and lambda 1. Then yeah, we can easily confirm that such kind of mapping, or such kind of definition for this one as M1, or let's say M0, and this one as M1, is compatible with the new definition of the measurement. So let's say that yeah, in the new definition, P of M is mainly defined as the P sub M dagger, P sub M psi. But we know that this kind of projection operator will be is the Hermitian. So yeah, P sub M dagger is the same as the P sub M, and then we know that square of the projective projection operator is just by itself. So yeah, it will eventually becomes like this one, which is the same as what you'd expect with the projective measurement. What about the result of the measurement? So we know that once we collapse to one of these, then it will be either become zero state or one state. But a zero state can be also considered as the P0 of the psi naught, because sorry, not psi naught, some the quantum original quantum state, because that if we apply the projection operator on some arbitrary psi equals alpha 0 plus beta 1, then by applying this projection operator on this state, only this term will survive. So this one is not properly because it will come out like this one. So it is not properly normalized. So what we have to do is calculate the magnitude of this vector like this one, and then divide by entire thing. So that's how we can obtain this eigenvector. So what I can show you here in this page is that the projective measurement can be always reformulated in terms of the new definition of the measurement, and so therefore the new definition of the measurement is superset of all the possible measurement in the quantum mechanics. As the projective measurement is one type of the generalized quantum measurement, another type is called as POVM measurement. So before I start, I explain about the POVM measurement. Let's reconsider the original definition of the third postulate, or description of the third postulate, and then again, the third postulate generally gave us two types of information. First was the measurement statistics, meaning that the probability to measure certain outcome, and then another information is the quantum state after the measurement. So in POVM, POVM is the acronym for the positive operator valued measurement, and then I will define what we mean by the positive operator. But the point here is that we only care about this probability, which is the first part, and then we are not interested in the result of the measurement. So in this case, we only care about this part, and then we don't care about this part. And then we might, you might realize that then, do we really need to use the M sub M? Because all that appears will always appear in the form of this the Hermitian conjugate of itself, and then multiplied by so Hermitian conjugate of the M will be multiplied to itself. So this is always this is the typical case which will appear all the time. So we will another option is we can just define this part as a new operator instead of writing in this form, and then the completeness relation which I started in the first page can be reformulated in this way, and then the probability formula will be also converted into this shape. And then in this case, we call each of these E sub M as the POVM element. And then in the next page, I will prove that the formalism between this POVM form compared to the original form are equivalent. But if we just define this one as fundamental rather than this one, then all because in this case we don't actually have to consider about the quantum state after the measurement. So the overall formalism becomes simpler. And then again, the complete set of this E sub M is called as POVM. And then even the projective measurement can be also considered as a POVM, because you know that because of the completeness relation, if we just start with all the summation of all the projective measurement, they will become the identity. So you can either consider the projective measurement projection operator as the POVM element, or you can also consider P sub m as the is equivalent to M sub m, because that, you know, if we take the Hermitian conjugate of this one, then it is the same as the original one, and then the square of the projective operator is just a single projective operator. So the whether we consider this one as M sub m or E sub m, it actually doesn't matter. Yeah, so it's depending on your preference, you can just assume whichever direction you prefer. Then what is the definition of the positive operator? Some operator is called as a positive operator if it has a property such that if I'm given any arbitrary vector v, then whenever I calculate for any arbitrary given v, if I calculate this value, then it will be always larger than or equal to 0, and then it is a real value. Then this operator is called as a positive operator. And then based on the definition of the E sub m as the M sub m dagger M sub m, then even though we don't have any requirement for the M sub m, E sub m is turned out to be always positive operator, and the proof is straightforward, because to prove that some operator is a positive operator, then we should prove that the v E sub m, v will be always larger than 0 or equal to 0, and then the this can be proven by noting that this one can be replaced by this, and then if we define this part only as a new vector like a w, then this part can be also, if I define this one as a w, then this the rest of the other left part is actually the same as the w, bra w. Bra w. So that means that whatever, I actually don't know what kind of w vector it has. It is, but it is always true that it will be the inner product of the same vector, and then the inner product of the same vector will be either larger than 0 or equal to 0. So based on this one, as long as we have this shape of the shape of the operator, then it will be always larger than 0, larger than or equal to 0 for any arbitrary given v. And then also it is obvious that the operator defined in this way is always Hermitian, because the definition of the Hermitian is that if we can prove that the Hermitian conjugate of the given operator is the same as the original operator, and then if we multiply, if we apply the Hermitian conjugate, then we know that then the order of this operator will be changed, and then this dagger will be applied like this. But the double dagger means that actually they will cancel with each other. So it is again M sub m dagger M sub m, and then it is same as the original E sub m. So that's how we can prove that the operator, which is defined in this way, will be always positive operator and then Hermitian operator. However, I should also point out that whether the given operator is defined in this way or not, as long as we know that some given operator is a positive operator, then it is always Hermitian operator. So the positive operator is just a special case of the Hermitian operator, and then I will leave the proof as an homework. So what I just showed here is not the proof that the general proof that the positive operator is always Hermitian operator. So yeah, this is special case when only when the our some given operator is defined in this form, then it will be always Hermitian and then also positive operator. And then the yeah, but yeah, because you can prove that any arbitrary positive operator is a Hermitian operator, we can also say that even if we start with the definition that E sub m is just the arbitrary set of the positive operator, satisfying this condition, then we can also say that there will be always the measurement operator m sub as the set of the measurement operator m sub m. And the proof is quite straightforward because we know that this operator is a positive operator, and then we know that positive operator is a special case of the Hermitian operator. So we can also say that this is always the Hermitian operator, and then what that means is that we can always diagonalize this operator, and then another property of the positive operator is that we can always find the basis which will diagonalize the positive operator. So only the diagonal components will be non-zero. Moreover, if the if some operator is a positive operator, then if it is just a simple Hermitian operator, then we know that it can be diagonalized. And then all the diagonal components will be real value. But Hermitian operator by itself does not tell you the sign of this guy. But if it is a positive operator, then it is also obvious that all the eigenvalue will be also positive values. So it will be so all the eigenvalue will be positive, and then this can be also split into the product of these two, square root of lambda 1 and square root of lambda 1 and square root of lambda 2 and so forth. So it can be always decomposed into the product of the same product of these two operator. And then if we call this one as m sub m dagger and call this one as m sub m, then we can always convert any arbitrary set of the positive operator into the set of the measurement operator, like this one. Now let's consider some of the example of the POVM. So in the with the projective measurement, we generally don't consider about the non-orthogonal measurement of the non-orthogonal states, but because the POVM is a generalized form of the measurement, let's say that Alice will send the 1 qubit to Bob, and then that 1 qubit can be prepared in only one of the two states, which is either 0 or 0 plus 1. And then I will call this one as a plus state or psi 2 state. And then the problem is these two states are not orthogonal to each other. So as we already proven, the quantum mechanics does not allow us to measure the identify these two states with 100% certainty. However, it is actually possible to distinguish these two states occasionally. So the goal is Bob wants to perform a measurement which distinguish these two states only some of the time, not all the time. But whenever Bob makes the decision or a measurement, then he does not want to make any error of misidentification, meaning that if 0 is sent, then the Bob will definitely know that it is 0 or not clear. And then if this one is sent, then this will be either recognized, identified as a plus state, or I don't know, or he does not know. But when this is received, he will never identify this state as a 0. So it might be a little bit confusing, because if you are just familiar with the concept of the projective measurement, but POVM, if you just follow the formalism of the POVM, and then if I just define E sub 1 as the in this form, and then E sub 2 in this form, and then E sub 3 is just the rest of the part, like just subtracting the summation of these two from the identity, then the summation of these three will always make identity operator. And then based on this definition of the POVM elements, it is actually possible that if you are if Bob received the 0, then these measurements make sure that Bob will never identify this 0 state as the put sign 1, because probability to identify this put sign 1 as the put sign 1 as the 0 as the so the probability that Bob will identify this state as psi 2 is 0. So even though you might consider that if we have non-zero probability for E2, then you might consider that that corresponds to identify psi 1 state. It is actually opposite. So if you have non-zero probability, then this corresponds to identifying as a psi 2. And this one, if you have non-zero probability for E2, then that corresponds to identifying a psi 1 or a 0 state. So this corresponds to plus state. So and then and that is obvious, because when we start with the 0, then the probability, if you just apply this 0 to E1 in this fashion, then they will always become 0. So when E1 is measured, then it should be psi 2. And similarly, if we start with the psi 2, which is plus state, then this E2, the probability to measure E2 is 0, while the probability to measure E1 is non-zero. Here, I'm not saying that it is 100%, because if you just calculate for this, when you apply the 0 to E2, it is not 1, because so if you apply psi 1 to E2, psi 1, it is 1 plus square root of 2 divided by multiply by 1 over 2. So this is a probability which is less than 1. And then what happens for the rest of the probability? And then that's to measure the E3. And then when you measure E3, then or if Bob measures E3, Bob he actually doesn't know what is the state, but at least he doesn't make any mistake. So that's the beauty of the POVM. And then again, this kind of measurement does not succeed all the time, but at least it does not make any misidentification. And then how can we implement this kind of measurement? it is not trivial. And then the one thing which is not exactly the same, but one trial you might consider is that whenever you are given some qubit, then you randomly choose to measure either 0 or 1 basis, or plus or minus plus minus basis. And then it's not it is not fixed whether you will measure a 0, 1 basis or plus minus basis. And then let's say that you just randomly choose to measure either one of them with the probability of half. And then if you start with the so if you start with the 0, and then the and then let's assume that you measure 0, and then in that case it is not clear whether it was measured as 0 because you started with 0, or even if you started with the plus state, because there is overlap between the 0 and plus state, you will measure 0. So measuring 0 does not help, and then in that case you can consider that one as a E3. Then when can we actually identify? Let's say that you start with a 0, and then you measure minus state. Then it is obvious that so again we are randomly choosing these two bases, these two types of measurement, and assume that we just chose the second type of the measurement. And then even if we started with 0, assume that you measured minus state. In that case, you can be sure that the input state was not plus, because if the input state was plus state, then there will be no reason why we cannot measure the plus. So the fact that we actually measured the minus means that the input state was 0, not plus. Similarly, if you started with the plus state, and then if you measure not 0 but plus this one value, that means that you can be sure that the input state was not 0, because if we started with 0, then we will always for this measurement we will always measure 0. But because we didn't measure 0 but 1, and then that means that probably not probably, but Bob can be sure with 100% that the input state was the plus. So that's how you can achieve some measurement similar to POVM given in here. But you will also realize that if I do this kind of 50% of chance to measure either 0 plus 0, 1 or plus minus, then you cannot achieve this kind of probability. And then this probability, or this correct the probability to identify plus and 0 state is higher than this case. And then you can also prove that these values are the maximum case, maximum correct identification probability. And then that will be given as a homework to prove these relations. So in today's lecture, up to now, we mainly considered how to reformulate the postulate 3. Now, let's consider about the postulate 2. In the when I first introduced the second postulate, I actually intentionally didn't emphasize this part, which says the closed. But postulate, the second postulate actually said what second postulate actually said was the evolution of a closed quantum state is described by the unitary transform. So in other words, if it is not closed, then we cannot directly use this formula. It is not guaranteed whether we can use this one or not. So unfortunately, yeah, quantum mechanics doesn't tell us what happens if we have a closed, not closed system, or we generally call it as an open system. And then still, yeah, based on our experience with the closed system, we should try to guess, or we should try to extend the problem to the open system. And then in that case, the formalism we are using is something called as density matrix. So from now on, and I will introduce the concept of the density matrix. And then in today's lecture, I have a little bit limited amount of time, so I will just give you a brief introduction to the density matrix, and then we will discuss further about the density matrix in the next lecture. So how can we start, or yeah, what's the concept of the open system? So let's say that I have some yeah. So as I mentioned, yeah, in my lab, we are trapping a single ion, or individual ions. So we have multiple ions here, and then what we are and we use each of these particle, or each of these ion as a single one qubit. So let's say we might have 3 qubits, but what we want to do is we want to manipulate only this system, and then we only want to focus on these 3. But and then yeah, for our system, yeah, our ions are well isolated from the environment. But in many of the system, the each of these particles cannot be completely isolated from other surrounding part. Yeah, so let's say that yeah, if you have some kind of solid material, then even if your qubit is somewhere here, but it is surrounded by a lot of other atoms which cannot be easily controlled, because there are too many number of the atoms surrounding this qubit. So, and then in this case, you don't want to model each of these surrounding parts, because the number of the surrounding atoms are too many. So yeah, it is basically impossible to model all of them. The problem is this qubit cannot just stay there forever, just isolated, but it will always interact with other atoms, yeah, surrounding this atom. So we need some kind of formalism, even if the particles are entangled with other particles. So that's where that's when the density matrix is most useful. Another situation we might consider is that, let's say that Alice is on the Earth, and then Bob is on the moon, or somewhere far away, like Mars or somewhere. And then let's say that Alice and Bob created the entangled state, like this one, and then they are separated to far away. And then the communication between the Earth and the Mars takes very long time. So they actually cannot know. Yeah, and then yeah, let's say that yeah, there is no communication channel due to some kind of whatever reason. And then in that case, even though we know that the qubit on the Alice side, or on the Earth, and then another qubit on the at the Bob side, or at the Mars, they are actually entangled in this way. But from the perspective of Bob, he actually cannot know anything about the Alice. So it is possible that Alice might already made some kind of measurement, or even when Alice is making the measurement, she might use either 0 or 0, 1 basis, or she might use the plus minus basis. And then because they cannot actually communicate, from Bob's perspective, Alice's state is completely unknown. Yeah, and then yeah, again, Alice might not do anything. Yeah, so Alice might just leave the qubit as it is, and then she does not try to measure at all. So how can, yeah, and then from the perspective of the Bob, he still needs to model what he has. So how can, yeah, so we might also assume that yeah, let's say that Alice actually measured the qubit along the 0, 1 basis. In that case, it is possible that Alice might measure 0, which means that the quantum state of this one collapsed into 0 with the A and then 1 with the Bob. And then in that case, what Bob will be left with is the 1 state, while if the Alice measures 1, which means that the quantum state collapsed to the second part, and then that means that Bob will be left with the 0 state. So we know that each of these cases will happen with the 50% of chance, because this is the coefficient in front of each of these terms, and then the square of this is 0.5. So we know that there is a possibility or probability to occur the first case with the 50%, and then the second case will also happen with the 50%. The problem is, from the perspective of Bob, he actually doesn't know anything about which one was determined. So yeah, in that case, what is the best way to model the state? And as I said, density matrix formalism is one of them. And then in the density matrix, what we do is, because we know that we have the 50% of chance of one state, and then 50% of chance, chance of 0. In this case, what we do is write this situation in this way, meaning that if we have 50% of chance of 0, then we are not just writing the 50% multiplied by 0 cat, but we actually also multiply the bra in this way. So we are creating the outer product. And then for the one case, we have also another 50% of chance, and then we start with the cat and then multiply by bra. And then in this case, yeah, this is actually operator, not the vector. And then we can also express this one as in terms of the matrix form, because it is operator. And then if you just write down, then this is the form of the matrix. The problem is, it is not, Bob does not know whether Alice will measure either 0, 1 basis or plus minus basis. So is this a valid formula? Well, if you see, if this is the first time you see the density matrix, then you have a lot of concern. But what is surprising is that even if Alice measure in different way, like plus minus state, she will be left with the same form of same density matrix. So yeah, let's say that Alice measures along the dA basis or the plus minus basis, and then we know that this psi minus state can, yeah, and yeah, let me first define. Yeah, so here D means that the square root of 2 and 0 plus 1, and then the entire diagonal means that square root of 1 over square root of 2 and 0 minus 1. So and then we learned that this psi minus state can be still will appear as this kind of a minus sign, even if we are using different bases like dA. Let me just use the plus minus state, because dA might be a little bit confusing. Yeah, so yeah, let's say that this is defined as plus state and this is defined as a minus state. And then even if we re-express this psi minus state in along the plus minus spaces, they will actually appear as the same as the plus plus A minus B minus A and plus B state like this one. So this is a well-known property. And then yeah, we already proved, we already showed this relation with polarization in the past. So how what will be the result of this what will be the density matrix corresponding to this case? Surprisingly, we know that from this result, we know that there is 50% of chance of happening this one and 50% of chance of happening this one. So what we can say is with the half of the property, Bob, the state of Bob can be either +1 or with the half of the probability, Bob's state will be minus state. And then if I just follow the formula of the density matrix, then density matrix, what density matrix says is so what it says is B should be half, and then I will just omit the subscript B because it is obvious. So in this case, it will be plus and half minus. And then if I expand all of this, then we know that the plus state is defined in this way. And then if I have plus plus cat and plus bra, then each of them has the factor of these, so it will be squared. So it will be another half, and then the term will be 0 plus 1, and then the 0 plus plus 1, and then what about the second term? Yeah, it will be another half coming from here, and then because this one also has a 1 over square root of 2, so it will also appear as the 2, and then it will be 0 minus 1 multiplied by 0 minus 1. So if we expand the entire part, and then we have all of this factor of 1 over 4. So let me just collect the entire part with this one. And then for the first term, it is so it is 0 0. So we will have 0 0, and then this will be multiplied to 1. So it will be 0 1, and this 1 will be multiplied to here. So it will be 1 0. Finally, we will have 1 1 state. Then what about the second product? It will be the same as 0 0 0 1 1 0 1 1, but there is a minus sign. So the difference is the same minus plus, like this one. So these are the summation, and then if we because these terms will cancel with each other, so the remaining term will be 2 of the 0 0 and 2 of the 1 1. So that 2 factor will cancel with this partially cancel the denominator. So eventually it will turn out to be half of 0 0 plus 1 1. And surprisingly, this is exactly the same as this one. So whether we start with the 0 1 basis or plus minus basis, the end result will be always the same as the yeah, same as this one. And yeah, this is not only limited to plus minus state, but whatever you choose, yeah, they will be always the same. So, and then yeah, even if Alice does not do any measurement, still the formalism of the density, the result of the density matrix will be the same. So in the next lecture, I will continue, and then yeah, I will continue from here, and then you will see that density matrix is very versatile in many of the situations.